name is Sonny Vidović, coming from the United States, Austin, Texas. I'm your colleague. Very puzzled with these presentations because it's a lot of theory. A lot of theory. X-ray, lead, well, that's all a great deal. But if you're a real engineer, I hope you get your gear and start doing your job based on all this jumbo mumbo that you just heard. Let me based on a couple of factors. As engineers and designers, you need to know a couple of things. You need to know what really makes people happy. All this performance, you know, I heard all these nice presentations, but nobody mentioned the money. You know, I have people working for me, and they don't care about temperature comfort. They don't care about noise. They don't care about subjective feel of how they gonna interact, drink coffee, what they're gonna do, are they gonna do, have fun or not during the breaks. They just care how much money they get paid. So let's get this thing in perspective, and then put that perspective in the real world of us engineers, design engineers who need to align with all these theoretical approaches of getting everybody happy. So how do you make happy people? What is the deal here? You know, make a rule, go publish to your ASHRAE journal, and they say that's how we're going to do it? No, it don't work like that in the real world. It don't work in the United States. Maybe it does work in Europe, but if you travel around to Europe, you're going to go to every single airport that does not have no thermal comfort. So I have no idea what's going on here. Anyway, the chair just told me you got 14 minutes exactly, so let's get going. My presentation helps the young engineers how to do the thinking, critical thinking, and make everybody happy. So we're going to be focusing on single VAV air terminal devices, which is about 90% of the buildings that we have, and that's how we control all these aspects that you heard about. So controls, everybody's familiar with controls. You heard about all these names, Siemens, Andover, Johnson, whatever. And everybody is also smart, but nobody still hit the target. So what do I, as a design engineer, I get to meet the owners, and the owners used to say, okay, this is what I want. I don't want to pay tons of money on anything. I want to have a good building that people's going to do the jobs, and I want my electricity to be low. So when anybody tells you that energy is just a 0.1%, I never met that kind of guy yet. So they said, make the building functional, make the building operational, make the building perform, and yeah, we can get the plaque, we can put it right on it, but you know, we really don't care about it. So how are you going to do that? So as you can see here, purposely I jumbo mumbo the whole thing that they say. I said, yeah, give me occupants not to complain, which means don't call the maintenance department all the time to complain about noise, temperature, effort, all these things that you just heard. So make it happen. Yeah, I'm gonna publish the code, and what are you gonna do? How are you gonna make it happen? So you gotta have some kind of standard, some kind of limit, some kind of expertise to make all these things be real. So comply with the required ventilation code. Yeah, ventilation code is measurable, everybody knows what it is. If you went to school, you kind of learn what it is. Great. Capture all possible energy savings. Oh, yeah, that's the money. That's what we're talking about. And then it's related to the next one. Basically, that means turn the fan down, turn the reheat down, turn everything down as possible so nobody still complains. So, typical diagram, to just go quick through it. This is the typical diagram. All of us engineers like to see the pictures. We see the pictures, we understand. So, when you go on the right side of the curve, it's very hot in the space, you're on the cooling. When you go on the left, it goes the opposite. There's one dead band right there. That band is between the heating and cooling. Now, the lower axis says 70 to 75 degrees. That's what everybody's happy, really. 70 to 75. But we purposely did 70 to 75 because 70, we want to have a set point and when we are cold. We don't want to heat them on 75 all the time, like in Heathrow. For whatever reason, they're doing that. So on 75, we're going to cool them, and on 70, we're going to heat them. Those are the two set points that I have to be, and I have to stand on it. Now look at that gray area that I put it in. That is the reheat energy. That's the money, folks. That is what we have to shovel it down. So how do we do that? That's the typical diagram. So let's go through it into the tactics how we can do. I just explained that, so you can just follow that. So how do I select? So the question is, am I, as engineer, as any engineer who works for me is going to say, well, how do I do that? I said, well, we learn in school how to do the maximum. Yeah, it's very simple. You just put your loads together, put a couple pluses, and you get the kW or tonnage and whatever you want to talk about it, and that's what your load is. So get me the terminal device that's going to provide me with the cooling that would match the load. Okay, piece of cake, 10 minutes job every space. Put it together, you got it, you're an engineer. Now it comes to the real question. Okay, what's the minimum flow set point? How do I do that? I don't know, I have no idea. Nobody told me about it. I guess terminal for whatever, let's just talk about. So, the two facts, I have to control that, and I have to still meet the ventilation code, because the ASHRAE guide in the United States are theoretical gurus who wants to make our life miserable. So, what is my controllable airflow? That's the key presentation fact. So I can use the couple sensors on the different sensors. All these years before, in the last century and this century, we always depended on the pressure differential as a key element. It's very easy to measure, go to the velocity, you get it. Well, all sensors, and that was the last year presentations that I presented, the thermal dispersion, that we closely work with the Eptron and Air Monitor and Onicon now. And the device that measures the thermal dispersion, it was not the target of this presentation, measures the velocity all the way down to 100 feet per minute. Now, since I have that great beneficial sensor that can do the 100 feet per minute, my minimum can go all the way to 100 feet per minute, which is very low. Now, how do I implement that? Typical examples is, see the circle, the blue area, it's with a normal sensor that probably 95% of the United States building use. Minimum is 450, 500, people lie about it, so let's get an average of 450. If you compare with the thermal dispersion sensor, you can see that the minimum controllable, it's all the way down to 100. So those two areas are getting a lot better. If you compare just the two diagrams, you're going to see the savings in the gray area. Gray area is the reheat. Remember the reheat. That's going to come back to it. So the reheat gets shrunk. So we keep going. So now we come to the factor that everybody's confused with the industry. What is that ventilation code? That fabulous ventilation code that they just pop up some number and then we're supposed to know what it is. It's two parts. One part is required by the CFM per each person that is in space, which is whatever, depending on the space, blah, 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 5-6 CFM per head. Very simple. You just add the table. Now, the other factor that nobody understands, it's the B1, which is my positive pressure. My main goal as a design engineer is to keep the building positive, never to get it negative. Nobody tells you that when you design. So that's the fact. So remember that B1 and B2 are very critical factors in the ventilation code that you gotta have all the time. The red line on the diagram represents my sensor. That's how low my sensor can go. That's that turn down, 1 to 10. I can really go low. Remember, if I go to the blue, what is the blue? What is the black? I can't see from here, so let's help. Okay, so the blue minimum rate, the blue factor, right there, the blue line represents how much air I have to bring to the space to have my ventilation code. Remember, ventilation code, that's a B2, it's related to the people occupancy. Now, if I don't have anybody in the space, I don't have to have that B2 anymore. I can do just B1, which is keep my building positive. So no environmental, no anything around, no humidity, nothing penetrates to my building and push everything out. Now, I can go that with the blue line. So, if I know this, my sensor can go to 100, I can do black, I can do blue. What do I do? In Texas, we really struggle with the terminology, what to call occupied, unoccupied, all these UK ideas. So we came up to the very simple thing and instead, let's split it to the work on and work off. Work on, everybody understands. Any Joe Blow can understand that work on means basically occupied hours and work off means nobody's home. If you think logically, work hours are only 8 hours. There's another 16 and nobody home. So that performance and all that, how that applies, that's 1/3 of the importance and 2/3 of non-importance, what I spend energy to. So we define it work on, 7 to 7, work off, 7 to 7, the opposite, PM, AM. And understand that the work on mode can be people in the space, people out of the space. Now when I split that and dissect it in a very understandable way, I can see that my work on can be based on B1 or B2. So the B2, as you remember, is a factor of ventilation code that can be detected in many different ways. And work off, I really don't need anything except my positive pressure. So, unoccupied strategies. See that diagram? It says very easily how low I can go. I can go to nothing. Keep to my building positive pressure, my reheat energy is shrunk. So, okay, I'm glad we spent time on the theory, but we don't want to do it in practice. Unoccupied strategy, so the stretch band. Remember, when unoccupied mode with the people are not in, I really don't care about temperatures. Only thing I care about how my system will recover. So I can stretch that 70, 75 all the way to 65, 85. If I just let it go to nothing, it will take more time to recover. The building might eventually get affected by that. So the next one explains the work on mode. How do I detect the people? You guys all know there's a million sensors that can sell you. You can do the lighting switch, you can do the CO2, you can do the million ways. In 5 minutes I just cannot even go through all this, but you understand what demand ventilation is. So that's that B2. Now look at the blue, black, and red. Those are all strategies that we can go. So my goal is to shrink the reheat energy. Remember, if I use the sensor who has a no turn down, who gives me the maximum of controllable rate of 500 feet per minute, most of the time of my life of the building will be in the reheat. Reheat is the money. Reheat is where we can say we can shrink that, we can push it to the left and control the reheat temperature to 9 degrees. 2/3 of the time I save the money. Now, the question is, can we go with a 0? Yeah, you tell that to the lead and they're going to freak out. Tell that to any code, they're going to say you're crazy. But why not? There's nobody there. Why would I have to condition my space? Why would I care about it? But 2/3 of my time, there ain't nobody there but the janitor. So, push it to the limit. So what we do, the strategy, we just control the surrounding the building, outside the envelope, and we turn down everything on it. And then we stratify that when the work on starts. If the work on starts at 8, I can push back from 0 to the minimum controllable flow of the pressure at 6 o'clock a.m. At 7 o'clock I can bring it down to the B2 and I can do rock and roll. Engineers' concerns? Oh man, one. Okay, so the problem with this, turning it down and all that stuff and great and dandy deal, like to make an illustration, you have a conference room that seats the 100 people. Conference room is occupied at 3 o'clock p.m. to 3:30 when everybody yells at everybody. but the rest of the time it's never in use. So technically I can turn it down all the way to B2 controllable pressure. I don't need the ventilation code in it, and I can even stretch the temperature if time allows. So the problem with this is the minimum air movement. If you have a minimum air movement, you're going to cause the problems. You gotta, as an engineer, and if you understand what you're doing, you gotta size the devices who can adequately distribute that air through it, and then it comes that air change effectiveness that you heard many times today. That really doesn't matter in 2/3 of the time. And engineers' concerns are addressed. Remember, those are the couple things that we made the mistakes during it. If you have a few zones, don't use it. You know, kind of think about it differently and strategically position your devices, what you're going to control and what you're going to select as devices. Now, this is those strategies, what you can use to help yourself and to find the different approaches to it. You can backset the temperatures, you can stretch the bed band. Those are all advanced logics that you can probably research on yourself and do the more difficult part of thinking, how to align yourself with all this well and all these things. So, questions? 10 minutes.